Okay, so today's lecture, as I said, two parts. In the first part, we'll do a review of some of the topics we covered and didn't get to finish last lecture on the subject of numerical integration. And then finally, we'll end on this subject of solving systems of equations in this algorithmic way through the finite element method for 2D and 3D problems. Now, diving right into some of the details of what we concluded on last time. If you remember, we went through this exercise where we said, let's take a single two-dimensional quadrilateral finite element, and let's test what happens if we choose different numbers of integration points to try to compute the stiffness matrix associated with this single quadrilateral element. And what we found is that, depending on the number of integration points that we chose, we found that, under subjecting this element to different modes of deformation, which could include things like rigid translation of the element, rigid rotation, those particular rigid modes of deformation induced no internal states of strain or stress in the element at any of its integration points. And so we concluded that these modes of deformation are totally unresisted by the element. So if we tried to subject the element to these modes of deformation, it won't generate any internal states of strain or stress that would attempt to resist those motions. So in other words, sometimes people call these modes of deformation zero energy modes, basically because they induce no internal strain energy within the element when you subject the element to these particular deformations. So they're totally unresisted. And that's good. We don't want the element to resist rigid motion. If it's not constrained against rigid motion, it should be allowed to just fly off and do whatever it likes. Now, other modes of deformation that resulted in a constant or uniform state of stress throughout the element included things like uniaxial stretching in the X or Y directions, or potentially pure shearing deformations. And it turns out that, in these uniform states of, uniform strain or, uniform stress situations, as characterized by those three particular modes of deformation, we noticed that it was sufficient to just use one integration point to represent what was going on in the element. Because the stress and strain throughout the element was the same everywhere, we could just use one integration point and we would capture everything there is to know. And each of these different modes of deformation was properly resisted by the element. The area where this became a problem was in these so-called bending modes, where if I tried to subject this element to this non-uniform deformation such that the strain or stress that would vary through the element should vary linearly through the depth of the element, let's say, as you might have in some kind of bending deformation. If you think about bending of beams, the classical assumption of beam theory is that the strain, the axial strain and the axial stress through the depth of the beam varies linearly. It's zero at the middle, and it's, maybe a maximum or a minimum at the top or bottom, extreme fibers of the beam. And a similar situation arises in these kind of quadrilateral elements when we subject them to these quasi-bending modes of deformation. We expect that kind of same linear variation through the thickness of this element. But what happens right at the middle? Right? What's the state of stress right at sort of the neutral fiber of a beam? It's just, it's just zero, hence the name, the neutral axis or the neutral fiber in a beam. Basically, there's that neutral fiber doesn't feel anything. It kind of thinks that there's nothing going on. And so the same is true in these elements where if we were trying to put an integration point right in the middle of the element, and if we tried to subject it to this bending deformation, then according to this one-point integration scheme, it doesn't think that there's anything happening in the element if I try to subject it to that kind of bending mode of deformation in either one of these two different bending modes, which basically means that these modes of deformation are totally unresisted by the element, which is problematic because obviously it's not that these elements should have no resistance to this. It should certainly resist these bending modes of deformation. And the only way that we can ensure that that's the case is by using a sufficient number of integration points placed not at the center, but rather positioned at these other integration points. So they properly sample the deformation that's going on, and the resulting stiffness matrix does correctly resist these bending modes of deformation. So our conclusion was that we needed enough integration points to ensure that our element was able to resist all different possible states of deformation apart from these rigid body modes of deformation. So the element shouldn't resist rigid modes of deformation, but any other type of deformation that the element might be subjected to should be resisted by the element. And to ensure that, we need enough integration points. Now, the heuristic in this case is that 4 integration points was sufficient for this 4-node quadrilateral element. Now, the question becomes, how do we generalize this finding to other types of elements that we might deal with, both in 3 dimensions and maybe other types of elements, even in 2 dimensions, which might have more than just 4 nodes just placed at the vertices? What if I had this interesting 9-node element where I have effectively nodes placed at the vertices? I also have nodes placed at the mid edges, and I might also have a node placed right in the middle, kind of in analog to that, 3-noded quadratic element that you considered in the last homework assignment. So it's sort of like the quadratic extension of that 3-node quadratic element into the 2-dimensional context, now including 3 by 3 sets of nodes. So in other words, 9 nodes in total. Now, there is a nice heuristic to try to understand how many integration points does this new 9-node element need in order to ensure that all of its modes of deformation will be resisted properly, through our integration rule. And the general heuristic is that you typically want as many integration points as you have nodes. So there's some reasons behind why that is. But really, if you take that away and you kind of say, okay, if I'm using these standard either quadrilateral or even linear elements, or potentially even 3-dimensional elements like hexahedra, in general, that's typically the case. You want to have about as many integration points as you have nodes in the element. So a nice heuristic. So in the case of an 8-node hexahedral element, for example, in 3 dimensions, you would want 8 integration points using a 2 by 2 by 2 Gaussian integration rule. So that's, the main takeaway. And if you use less than that, then you may run into trouble. You may run into this issue of, the elements are unable to resist certain modes of deformation. And what's really the consequence of this? If I chose to use some other integration rule that didn't fully integrate the element with a sufficient number of these integration points? Well, you could certainly try it. You could go to your finite element program, and if you have access to the internal guts of the thing, you could implement your own element. And you could try out using a fewer number of integration points than are required to resist these, particular modes of deformation, like the bending modes of deformation. And you might think, well, that should only affect the bending behavior of this structure as a whole, right? But in fact, if you have, let's say, a mesh that consists of, quadrilateral elements patterned in a nice regular rectangular grid initially, and if you were using an insufficient number of integration points in each one of these elements, such that, let's say, in each one of these elements, you only used 1 integration point placed right at the middle of it, what you'd find is that certain modes of deformation, the bending modes of deformation for each element, will be kind of weak. They'll be kind of allowing this element to distort or deform in that bending mode without any resistance occurring. And it so happens that if you pattern elements together in this way, this element and its neighbor might be allowed to deform in this kind of like opposing fashion, where they're both deforming in this particular unresisted mode of deformation, this kind of bending mode, but in this way that patterns throughout the entire mesh. So not only do you have individual elements that become unstable, but together, even when you pattern them into the format of this larger mesh, they might all become unstable. And they might all deform in this funny way. And typically the pattern that emerges looks something like a patterning of hourglass shapes. So typically, if you see this phenomenon occurring, people will refer to this phenomenon as hourglass deformations or hourglass instabilities. And it really refers to precisely this issue of under-integrating the elements, not using enough integration points to ensure that the elements are able to resist these modes of deformation. So it's a totally unphysical response, because certainly the elements And the structure as a whole shouldn't be exhibiting this weird oscillatory variation in the displacement field, allowing individual elements to do this. That makes no sense. It's completely unphysical and is a consequence of using numerical integration with an insufficient number of integration points. So you might say, well, we'll never have to deal with this, right? I'll just use enough integration points and be done with it. And I shouldn't have to worry about this issue of hourglassing, right? Well, that would be true, except for the fact that there are certain cases where, unfortunately, the finite element method succumbs to its limitations. And the main one that I'll point to is that really classical formulations of finite elements, as we've discussed up to this point, which are formulated through this method of supposing that the primary unknowns that we're solving for are the displacements at the nodes. So we characterize the solution unknowns by assigning discrete values of displacement to each node in the mesh, and then we characterize the displacement field within each one of these elements using sort of an interpolated representation of the displacement field using our finite element shape functions. Now, if we do this and we treat the primary unknowns in the problem as being these discrete nodal displacements, and the primary solution field of interest is the displacement field, we formulate our problem, we can create a Galerkin approximation to it, we can discretize it using finite elements and do all that. We can run an analysis and see, all right, let's use some finite elements to solve some real problems. We could even pick some really simple problems like a cantilever beam. Let's just choose some simple, relatively thin beam, mesh it with a few elements, and see what happens. We might find that at least in these kind of simple beam problems, we might think, well, we should get a pretty decent solution, right? I'm using finite elements after all. These are very sophisticated mathematical tools, right? Well, you might be surprised to find that for even relatively simple problems like the one shown here, the accuracy of using finite elements in these contexts can actually be really bad. And it might not be immediately apparent why that is. Some of it has to do with just the inherent limitations of this Galerkin approximation property and the best approximation property of finite elements in particular. Finite elements give you the best approximation possible that our kind of chosen, discrete representation for the solution is able to provide us. But it still may not be that good. It's the best approximation we can do with our chosen discretization of the problem, but sometimes it still gives relatively bad accuracy. So that's particularly true in these kinds of bending problems or situations, especially where the aspect ratio of the elements that you're using is relatively high. So if you have elements that look kind of like this, or worse, if you have elements that look like this, which are really long and skinny and have, an aspect ratio of like 10 to 1 or something really bad like that, the accuracy of using elements shaped like this goes way, way down. And there's a few reasons for that. It has to do with a phenomenon which we'll talk about in a future lecture called locking, which is basically a situation where there are certain modes of deformation which result in these kind of unphysical states of stress or strain that occur local to a particular element. And it has to do partly with the fact that if we choose to represent each one of these elements like this long, skinny bar, and if we try to subject it to a nice, let's say, bending mode of deformation like this, really, because of the way that we've chosen our basis functions, we're sort of constraining the element to always remain nice and flat like this. Even though we know that for a nice smooth curved beam or something like that, the true solution should look kind of like this. But our finite element basis functions are preventing this kind of mode of deformation from occurring. We just don't have a way of representing these nice kind of smooth or curved bending modes, which basically means, especially as you have these long, skinny elements showing up, you'll get really, really bad accuracy in using these conventional 4-node quadrilateral elements or 8-node hexahedral elements in 3 dimensions. So there are ways that you can get around some of these issues and still, get reasonable accuracy out of the solution. But some of the solution strategies to deal with these issues actually involve using less integration points. some of the issues that arise because, we're trying to compute a stiffness matrix for this element using the appropriate number of integration points. In this case, 4 integration points using our 2x2 Gaussian integration rule. But in some cases, that results in a stiffness matrix for this element, which is a little too stiff. And that's precisely the issue that we're trying to overcome. We want this element to not be so stiff so that it actually deforms and deflects the appropriate amount and more accurately represents the solution that we should expect to get for this nice, cantilever bending problem. So one solution strategy to attack that is to try to reduce the apparent stiffness of the individual elements. And you can do that by basically just using less integration points. And it makes the elements look less stiff, certainly. But obviously the downside with that is that maybe now the elements become unstable. They succumb to these hourglassing modes of deformation, as I kind of previously alluded to. So constantly in the battle of finite elements, there's this struggle between these two extremes. On the one hand, there's the issue of trying to ensure that you have sufficient stability in your problem so that you avoid issues like hourglassing and instabilities that might manifest because you're not using enough integration points. And on the other hand, you don't want the structure to look too stiff in an artificial way that depends on how you've chosen to discretize your problem because of, the finite element basis functions not being able to represent the true solution that you're seeking. So you don't want it to be too stiff. You don't want it to be too soft. That's the struggle. You want something nice in between that kind of balances the divide between those two things. And there are specialized element formulations that try to strike that balance appropriately. And we'll certainly discuss some of those, but in a future lecture. So we'll talk about some of the particular strategies that we can use to try to do something more like this, try to use one integration point, but also ensure that the overall element still remains stable and resists those hourglass modes of deformation. So there are some subtleties to the use of these integration rules and integration formulas. And there are even situations where people will try to get away with just using one integration point because it's just cheaper. If you have fewer integration points where you have to compute stress and strain within each of these elements, it definitely costs you less in a computational setting because I don't have to compute, 4 times the number of elements, the stress and strain in each one of these things. I can just compute one value per element and, move on with my life. And so there are good reasons to want to try to reduce the number of integration points for multiple reasons, computational cost reasons to ensure that the elements aren't too stiff, things like that. But we'll get into some of those details in a later lecture. Okay. Now, the last thing I want to talk about in relation to numerical integration is what do we do not just to compute the element stiffness. We talked about how do we assemble terms that relate to that internal force term that shows up in the weak form integral. We also need to integrate terms that contribute to external forces or equivalently lumped external forces applied at the nodes in the structure. Now, to do this, we came up with 2 terms that contributed to the resultant external nodal forces at each of the nodes in our mesh. And they had to do with integrating terms that depended on any externally applied surface tractions on the boundary of our body of interest, and also interior volume integrals involving this possibly body force term, kind of like gravity or something like that, that might be acting at all interior points within the structure. So there are 2 additional terms that we need to integrate using our finite element, technology and applying some of these things. The second of these terms is probably relatively straightforward to figure out. What do we do with that? And at the end of the day, if we have some body force, nominally a body force vector, but if it's gravity, then you can kind of assume that this body force vector is just a constant value. Okay, that's fine. Potentially, it could be variable. It could vary as a function of spatial position. But at the end of the day, what we need to do is just integrate over the volume, this body force vector times the nodal basis functions. We could integrate contributions to that, body force term, just like you did in 1 dimensions, by looping over the elements and going element by element and integrating terms involving not just the nodal basis functions, but the nodal shape functions. Some contributions to the nodes, and then you get the resultant answer. And to do that integration on an element by element basis, rather than integrating over individual element volumes and their distorted configurations, we can do that same change of variables that we did to try to transform integrals to compute stiffness terms. And we can basically use numerical integration in the same way. And notionally, the same integration formulas would apply when you're integrating these body force terms. If you had, let's say, an 8-node hexahedral element, you would want to have roughly 8 integration points that you would use to integrate these body force terms. All right, so that one's not so bad. The only one that we kind of have some trouble with is actually this one. How do we integrate surface forces? And more specifically, surface tractions, a force per unit of area acting on some kind of planar surface. Now, it might seem like, okay, well, we could do the same thing, right? We could say, rather than integrating this surface traction over this whole kind of exterior surface, we could break that exterior surface up into corresponding surface elements. So in other words, if we had a whole exterior surface of the body where we were applying some externally applied surface traction, we could look at that exterior portion of the boundary of the mesh and say, well, which surface elements? In 2 dimensions, these surface elements might be one-dimensional kind of line segments. In 3 dimensions, the surfaces of a 3-dimensional volume-filling mesh are themselves just 2-dimensional surfaces, right? The surfaces are kind of sides of different elements that might be exposed on the boundary of this mesh. Now, we could say, well, if I want to carry out these integrals, these kind of traction integrals over the surface of this, portion of the boundary to which I'm applying these traction boundary conditions, well, I need to carry out an integral not over a volume now, but over this surface. In 2 dimensions, that surface is just the 1-dimensional line. In 3 dimensions, that surface is now this 2-dimensional planar area. So how do we do that? Especially considering the fact that we definitely don't want to integrate these surface tractions actually in their physical deformed configuration. We'd like to do a similar thing to the way that we posed these integrals over element volumes. Do some kind of change of variables formula to transform integration over this weird, funny, distorted, quadrilateral patch in 3 dimensions and transform that into an equivalent integration over a nice, perfect square in this kind of particular surface element's parent or kind of a parametric domain. So that's really the whole idea behind computing surface integrals. By supposing that we can break up that exterior boundary to which we're applying tractions into corresponding surface elements, and then over each one of these surface elements, we suppose that the representation of that surface can be, interpolated just as we had for our 3-dimensional volume filling elements. We invoke the isoparametric mapping, in other words, to suppose that if I have this 1-dimensional element, then I can interpolate displacement over this kind of whole element using my finite element shape functions, 1-dimensional finite element shape functions in this case. Or I could also use that same interpolation scheme to interpolate the element's nodal coordinates over the full interior length of the element. And that's what gives me this isoparametric transformation, a mapping between these 1-dimensional parameterized series of points, parameterized in terms of just this one coordinate C, to give me what are the interpolated coordinates of some point that might exist in 2-dimensional space. Now, this is an interesting observation because now our isoparametric mapping doesn't translate between, let's say, C and eta, a 2-dimensional coordinate system, into X and Y in physical coordinates. Now we actually have just one parametric coordinate, C, which maps into 2 physical coordinates, X and Y, to denote that this line segment might not just be, oriented along the, X-axis. It might now be inclined in space. So reflecting the fact that now we have an isoparametric transformation that says, well, my line segment is really going from a 1-dimensional coordinate system now into this 2-dimensional coordinate frame. How exactly do I carry out my change of variables now? because inherent in the whole change of variables that we did to try to figure out how do we transform integration over the element's physical domain into the corresponding integration over the element's parametric domain. Now, that was simple because there was this one-to-one mapping between points in three-dimensional space to other points in a different three-dimensional space. But now we want to do that same transformation between points in a two-dimensional space back into points in this one-dimensional space. So the difference in the fact that there's like different dimensionality in these different parametric versus physical domains introduces some challenges for how we actually carry out this change of variables. But it turns out that it's not so difficult to overcome. We can still transform integration over this linear segment, which I'll call gamma sub e, the particular surface element, which might be a subset of the boundary to which we're applying these fractions. We can transform integration over gamma sub e into corresponding integration over the C domain, ranging from -1 to +1. So that's not so bad. We can even use our kind of change of variables to say, well, I can represent physical coordinates x directly in terms of this one-dimensional parametric coordinate C. Okay, so I can plug that in, and if there was some dependence of the shape functions or the traction vector as being a variable function of position, I can transform those dependencies into just dependence on this C coordinate, that one-dimensional parametric coordinate. Now, the last thing that we have to do is that any kind of measure of the apparent length, basically, ds, which I'll call basically that kind of measure of what's the length of this integration domain in one dimensions of this oriented line segment. It's kind of like saying, I want to integrate over this inclined line segment, but it's parameterized by this kind of one-dimensional coordinate C. How do I transform, effective differential lengths of this inclined line segment to corresponding differential lengths as measured in the element's parametric coordinate frame? Effectively, I need some way of transforming this small differential length of this line segment, ds, into corresponding, scaled representations of, the element's length in the parametric frame, dc. And that scaling term is directly dependent on the Jacobian of this isoparametric transformation, the partial derivative of x with respect to c. But note that this Jacobian isn't a matrix. It's just a single vector in this particular example. There's two components of physical coordinates, x and y, but only one parametric coordinate. So clearly, we can't take the determinant of this Jacobian matrix because to take a determinant, it would have to actually be equidimensioned. It would have to have as many rows as it has columns. But because it doesn't have an equal number of rows and columns, we have to do something different. We still have to do something that looks like, take something like the magnitude of this resulting vector in order to compute what's the relative scaling between parametric differential line segments to corresponding inclined differential line segments in the physical coordinates. And it so happens that the operation we need is really nothing other than this kind of vector norm. So if we have this Jacobian, which itself in this kind of one-dimensional case is just a single vector consisting of two components, dx dc and dy dc, we just have to compute what's the magnitude of that resulting vector. And then that actually gives us the appropriate scaling between differential line segments in this surface element's parametric domain compared to its actual inclined physical domain. So that's the simple way to do it in one dimensions. In two dimensions, when we have now this planar area, a similar concept and concern arises, where in this case, we have two in-plane coordinates, c and eta, parameterizing this surface. Here too, this surface might consist of discrete nodes, which might exist in some three-dimensional space. So each one of these nodes might have an x component, a y component, and a z component. But because we have only two parametric coordinates, c and eta, which interpolate this surface, given these different nodal positions, we need to figure out a way, how do we transform integration over this funny, distorted, and kind of inclined surface embedded in the three-dimensional space? How do we transform this surface integral into an equivalent parametric integral over a nice perfect square in a kind of flattened two-dimensional plane. And again, here too, we have to figure out how do we replace this dA, differential area elements that might exist in the element's deformed configuration, its actual physical coordinates. And the transformation involves simply treating that area scaling of small patches of area in the deformed configuration and figuring out how they relate to small perfect square differential area elements in the element's parametric configuration. That particular scaling actually arises by computing something slightly more complicated. If you'll note, this parametric mapping goes from 2 parametric coordinates to 3 physical coordinates, x, y, and z, which means that the resulting Jacobian of this transformation will result in a matrix that has 3 rows corresponding to the 3 physical coordinates and 2 columns corresponding to the 2 parametric coordinates. Again, kind of a mismatch in the number of x versus c coordinates. We can't take a determinant, but we can take some measure of this matrix. And it turns out that that measure that gives us the scaling between parametric area elements and physical area elements is precisely proportional to the cross product of the first 2 columns of the Jacobian matrix, dx dx and dx d eta. So take those 2 vectors, 3D vectors, compute their cross product to get a new vector, and then simply compute the magnitude of that resulting vector from the cross product, and that gives me precisely this area scaling that I need to carry out surface integrals. Kind of complicated. It's a lot of extra stuff that we have to figure out how to do these transformations of area elements to transform everything back into this nice parametric domain in 1 dimension or 2 dimensions. But at the end of the day, if we do that, then we can apply our classical Gaussian integration techniques over these nice 1-dimensional parametric domains or 2-dimensional parametric domains to actually carry out these surface integrals. So it's a lot of extra work that we have to do for doing these surface integrals, and some fancy transformations had to happen to be able to figure out how do we actually scale these things. But at the end of the day, it's not so much worse than what we had maybe had to deal with in the case of the 3-dimensional integrals or the 2-dimensional integrals for volume integration. All right. Any questions on this before we move on? No? Okay. Well, we might have a chance to revisit some of these subjects, but I do want to get through some of the subjects that we had promised as being the primary subject of today's lecture. So we talked maybe a week or 2 or more ago on the subject of how do we solve finite element systems of equations in sort of an algorithmic or procedural way. And I presented this sequence of operations to you previously, which entailed first defining some problem, then setting up the resulting linear system of equations, characterizing the finite element, Ku equals F externals, the matrix system of equations that arises from our finite element discretization of this problem. We then had to partition that system of equations and solve that, smaller subset of that system of equations to determine what are the unknown displacements in the structure. We could then go through some post-processing steps, determine what's the internal state of stress and strain in the elements, and then finally look at some of the results. And it turns out that this whole procedure, in the context of solving 2D problems or 3D problems, carries over. And all these steps remain more or less the same. There's only a few things that we have to modify now in the case of 2D or 3D problems. And we'll highlight some of those. But first, starting with how we define problems in these 2-dimensional settings. I'll use as a prototypical example this simple 2-dimensional patch problem, where I have a small square domain equal side length in the x and y directions, and subject to the following set of boundary conditions. Now, you'll notice I've specified boundary conditions everywhere on the boundary of this small patch. It's constrained against displacing in the x direction by these kind of rollers that still resist uplift. So it prevents displacement in the x direction along this edge. It prevents displacement in the y direction along the bottom edge. And everywhere else, I'm prescribing mostly 0 traction, except for this constant uniform tensile traction applied to the right-hand face of this square patch. I'm not using any body forces or defining anything funny. And I'm assuming that the material properties are constant throughout the interior region of this patch. Now, I need to actually, take this problem and say, well, here's my boundary value problem. I've been specific about where all the boundary conditions are defined. I've defined this domain in this nice continuous way. But if I want to solve a finite element problem, I have to translate this problem into an equivalent discretized problem. Somehow I need to take this problem and convert it into a finite element discretization, or a mesh consisting of some number of elements and some number of nodes connecting the vertices of these elements. So I can do this. I can say I've translated this domain that consisted of just a uniform set of material properties into an equivalent set of, in this case, just 4 elements and 9 nodes positioned at different locations. And I've also been a little bit funny. I've decided I was going to define my mesh in a way where it wasn't going to be a nice perfect grid. I was going to just take this center node at number 5 and perturb it a little bit just to see if that messes anything up or if that's perfectly admissible. I also have to translate how I was assigning those displacement boundary conditions. Rather than assigning constraints along the entire edges of this mesh, I actually have to convert those constraints into equivalent constraints just directly applied at the nodes. So rather than trying to say, I'm going to try to be, really meticulous and try to constrain these edges and be consistent with the way that I've originally defined this problem, that's really hard to do. And in general, instead of doing that, it's usually easier to just say, well, go to each node, and wherever it was constrained along the boundary, we're just going to enforce our displacement boundary conditions just at the nodes. So that's a crucial distinction. These nodes are really subject to the boundary conditions, displacement boundary conditions, and also any externally applied forces or tractions that might have been smoothly applied over this kind of exterior region. Eventually, those are going to get lumped into equivalent nodal forces, but we have to go through some kind of integral step. We have to use some set of, let's say, surface elements. In this case, we would need 2 surface elements connecting nodes 3, 6, and 9 in order to integrate the resulting, forces that should act at each of those 3 nodes through integration of the traction vector multiplied by the different nodal basis functions along each of those different surface elements. Okay, so we've discretized the problem. Let's step through a few of the details here just to kind of give you a sense. If I wanted to characterize aspects of the elements, or rather the nodes of this problem, I would need to just first come up with a node indexing scheme. So assign some labels to each one of the nodes in whatever sequence you prefer. It doesn't really matter. I could call it 1, 2, 3, 4, 5, 6. I could have gone 1, 2, 3, 4, 5, 6, etc., or any other particular ordering you like. But in any case, I can assume some particular ordering, and I can list off what are the coordinates of each one of these nodes. I can put that into the format of an array, and you can kind of see, for example, node number 6 has an x and y coordinate corresponding to this 6th row in this kind of coordinate array that are proportional to, L, the x coordinate, and L over 2, the y coordinate of that specific node. So I can compactly represent the coordinates of all these nodes in this compacted array, just for the sake of future reference and kind of determining which nodes live at which particular positions. All right, for the elements, similar to what we did in the one-dimensional context, I also have to specify element connectivities, which describe which elements consist of which nodes placed at their vertices. For example, element number 1 just consists of nodes 1, 2, 5, and 4. But remember, there was a canonical ordering to the way that we chose to list off those nodes. In the case of these quadrilateral elements, we had to choose the ordering of those nodes in a counterclockwise fashion. So if I started with listing off first node number 1 for element number 1, the next node I would have to list should proceed in this counterclockwise ordering. So the second node would be 2, the third node 5, and the fourth node 4. If I had, let's say, element number 3, as shown in this example, and if I was being funny, I decided, let's start listing the nodes for this element, but not, let's start with 4. Let's start with node number 8. I would then have to proceed in counterclockwise ordering, such that I would list off 8, 7, 4, and then 5. So I can list off this kind of cycle of nodes, and it doesn't really matter if I'd said 8745, or if I had said 7458, effectively they describe the same element. As long as I'm consistent with that counterclockwise ordering, it doesn't really matter. You could permute these nodes and as long as they're always in that counterclockwise ordering. Okay, I can list off the connectivity then for each one of these different elements in terms of those different 9 nodes and put it into this compact array. So each element's nodes are listed with the corresponding row indicating the particular element's index for 1, 2, 3, and 4. I can also list off different properties for each element. If I want to make the material properties different in different elements, I can do that just by assigning different material properties, the Young's modulus and the Poisson's ratio to be different. You could also put this into a nice compact array where the index of that array being corresponding to the element's index. All right. Now for assigning displacements. I could just, certainly pick off different components of displacement that I want to assign at different nodes. But in this case, I have to be a little bit funny in the way that I prescribe these different displacement boundary conditions. Not only do I have to specify at which node am I constraining displacement, but I also have to specify which component of displacement am I constraining at that node. So really, I need 2 pieces of information. To constrain the displacement at a particular node and in a particular direction, I need to know what is the node index, let's say, node number 4, that is being constrained, which component of displacement is being constrained, either x or y. And in this array, I'm just saying an index of 1 indicates I'm constraining x displacement, an index of 2 indicates I'm constraining y displacement. And then finally, I have to specify what is the constrained value of displacement that I'm putting at this node. In all of these cases, I'm prescribing a value of 0 displacement. So I can just say for all these nodes, listed in this array, I'm prescribing just 0 displacement at each one of these. But it's important that now that we have multiple degrees of freedom that we could constrain at each one of these different nodes independently, I have to specify not just the node index, but also the degree of freedom index, or the dimensionality of the direction of the displacement that is being constrained at that node. And certainly you could constrain both. Node number 1 is constrained in both the x direction and the y direction, but I actually have to have 2 entries here. So double counting node number 1, but constraining independently its x and y displacement. So it's a little bit funny, but certainly that gets a little bit trickier in 3 dimensions, or if you have other types of degrees of freedom at these nodes, like rotations and stuff, then you have to account for a bunch of different degrees of freedom that can show up there. All right, but in the end, you just have to list, which nodes are constrained and which degrees of freedom at those nodes are constrained. For prescribing tractions on, let's say, this edge of the mesh, over which we assume that there's this constant traction that we're applying. If I assume that the traction acting on each one of these small subsegments or surface elements, as I'll call them, if I know that the traction over each one of those surface elements is constant, then all I need to do is first define what these surface elements are by specifying their corresponding connectivity. So surface element 1, denoted by gamma sub 1, is this surface element that has nodal connectivity nodes 3 and 6. Surface element 2 has connectivity 6 and 9. So I can list that off just like I did in describing the connectivity of these quadrilateral elements. I can do the same thing for defining these surface elements, but where the surface elements only have 2 nodes each. I can also list off what are the corresponding components of traction assigned to elements 1 and 2, where maybe I can also compactly arrange that into the format of some array or something like that, where the row of this particular array indicates the corresponding surface element, the second row being surface element 2. And in the particular entries of this array, I can list off the different components of the assumed constant traction vector that acts over this surface. So in this case, it has a constant x component of traction, and there's no y component of shear traction. So I can basically say that there's a force per unit of area that's acting normal to the surface or in the x direction, p sub x, but no y component of traction. So just specify that y component to be equal to 0. Okay, so that's surface tractions and how we define all these different quantities of interest on this mesh. Now we actually have to assemble the resulting system of equations. And we do that by setting up some global stiffness matrix, some global external force vector, and a vector of nodal displacements. For the stiffness matrix, we have to create a matrix that has an appropriate size proportional to the total number of degrees of freedom in the entire mesh. And that number of degrees of freedom is directly proportional to the number of nodes times the number of degrees of freedom that exists at each one of these nodes. In this case, if each of these nodes can only displace in the x and y directions, then really the number of degrees of freedom is proportional to the number of spatial dimensions in this problem, or n dims here. So in the end, if I have 9 nodes and 2 spatial dimensions, or 2 degrees of freedom per node, then I have a total of 18 degrees of freedom in this entire mesh, which means that the resulting stiffness matrix should have dimensions 18 by 18. And I could represent that, listing off all the discrete components of the stiffness matrix individually, or I could note that, if I write the stiffness matrix in this format, then each one of these sub-entries, where let's say each one of these sub-indices ranges A and B over the number of nodes in the problem, then this small sub-matrix indexed by A and B is itself a small 2 by 2 matrix corresponding to the x and y components of displacement that might happen at nodes A and B. Okay, so to assemble the stiffness matrix, I have to do precisely that same procedure that we talked about previously. I have to loop over all of the elements, and then for each element, compute that element's local stiffness matrix. In this case, these kind of quadrilateral elements should have a stiffness matrix that is dimensioned to be of size 8 by 8, proportional to 4 nodes per element times 2 degrees of freedom per node. So I can pattern it kind of in this format, noting that each one of these submatrices is itself a small 2 by 2 array. And I can compute these specific entries using that formula that we had previously derived and developed. That integral over the element domain involving B transpose sub A, dotted with D, the constitutive modulus tensor, dotted with B sub B, these kind of strain displacement matrices, and integrate that whole thing over the element to get just this one contribution, K sub AB. Do that for all values of A and B ranging from 1 to 4 for this element. And then I have to figure out, where do I sum these different contributions, these element stiffness matrix terms, into the global matrix, the global stiffness matrix. And that mapping of local element node indices to corresponding global element node indices can actually be determined precisely by, going back a few steps, precisely by this array, the element connectivity array. Remember this thing? It was the thing that we said gave us a way of listing off specific local node IDs, nodes 1 through 4 for this local element are actually corresponding to global node IDs 8, 7, 4, and 5, which means if I wanted to figure out for element number 3 in this example, which entries should I sum, let's say, the local node IDs 1 through 4 for this element, which IDs should I sum into in the global array? Well, it turns out that if I have this particular row of that connectivity array corresponding to that list of node IDs for this element, then precisely these are the node IDs that give me this mapping from local node IDs of this element to the global node IDs that need to be, matched up in the global stiffness matrix assembly procedure. So if I treat this kind of vector, of values, in other words, as kind of being the range of sub-indices over which I would have to kind of loop over in summing contributions to the global system of equations, then it turns out that I can match up, global node number 8 corresponds to local node number 1 for this particular element. Global node number 7 matches with local node number 2 for this element. And in that way, I can figure out which of these entries do I need to sum these, local element stiffness contributions to into the global system of equations. And using the element connectivity array is a really nice way of figuring out how to do that transformation and how to figure out where those stiffness contributions should go. All right. You can do the same thing for external forces. Initialize the vector of external forces to be 0 initially, dimension it to be proportional to the total number of degrees of freedom in the whole problem. And the process of assembling the system of equations, or rather the external forces that arise from applying external tractions, for example, is fairly straightforward. I can loop over each one of these surface elements to which I'm applying, let's say, a constant traction. I can integrate that traction over the element multiplied by the corresponding element shape functions for each one of its nodes. And then I can use the surface elements local to global nodal connectivity to figure out which entries of this kind of external force vector, which nodes in the global vector of external forces correspond to the local nodal forces of this particular element that I've done this summation for. And I can figure out where those need to plug in. So a similar concept applies when you're trying to go from local surface element node IDs to global node IDs in this whole system of equations. And the last thing I'll end on is just figuring out how to assign these discrete values of nodal displacement at each one of these different corresponding degree of freedom IDs in this big vector of displacement degrees of freedom, where the vector of displacement degrees of freedom is also of length 18 by 1. So there's a total of 18 degrees of freedom. There's the x component of displacement here, the y component of displacement here, then x and y displacement here, and x and y displacement at node 3, and so forth. And it's all sequentially listed in this array. But the question is, if we have our specification of constrained displacement degrees of freedom in each one of these different nodes and in different directions, in different degree of freedom directions, how do we figure out where we should actually apply these corresponding imposed displacement constraints? How do we know which index in this array we need to actually set these values? And if you have some of those details, if you know which node is being constrained, in other words, the A index of a given node, and if you know which degree of freedom index is being constrained for that node, in other words, the I index, then you can figure out exactly which index in this global array is the one that you want to constrain by using this simple formula. So relatively straightforward if you want to go from a node ID and a displacement degree of freedom ID and figure out which component of displacement in the global array does that correspond to. You can just use this formula and kind of plug it in. All right, so that's where we're going to end it today. We'll kind of pick up on Friday with some of the details of actually running some problems and getting some interesting results. All right, until then, I'll see you then.